Okay, guys, recording the podcast to homework. See here, I believe this is homework 3.6P. These questions have to do with two structures that have the same elements: carbon monoxide, CO, and carbon dioxide, CO2. And it says assume that both structures exhibit ideal gas behavior. This is not something that we need to know for this unit. We will get to gases later, though. I will take this opportunity to tell you, though, that oftentimes I have to do this. And what that means is the people who write the AP test like to ask you different questions from different units in one free response package. So oftentimes you'll have to draw a Lewis structure, and then you'll have to do perhaps an electrochemistry problem or a thermodynamics problem or an equilibrium problem. So it's just a good opportunity for you guys to be ready for that and used to that. So the first question says, draw the complete electron drop dot structure for CO and CO2. So before you draw CO, I want to let you know that this is something that is new. I want you to be aware of that. I will teach it to you in class. It's going to involve something called shifting instead of splitting. And if you refer to your flow chart, you'll notice that the question asks, if you dead end, can you shift? And you can't shift, you split. So this is the first time that you're being exposed to shifting. I'll show it to you in the podcast first, we'll do it in class, and we should be good. So here we go. Skeleton structure for C. Let's do CO2 first. Okay, since that's the easy one. So we're going to do CO2 first. Skeleton structure. Lone pair electrons. Valence electrons. Connect the lonely dots. And we are on a free response question, so we're going to draw it over nicely. For CO, carbon monoxide, we have C, we have O. There's our skeleton structure. There's our lonely dots. And here are our lone pairs on oxygen. Okay, so watch carefully. I'm going to connect. I'm going to connect. Okay. Now I just hit a dead end, and what would be a tempting thing for you guys to do would be to split up both of these electrons immediately. If you notice you do that, you're going to have 4 bonds on a quadruple bond between C and O, which is not possible. So we're going to do something called shifting here. And in shifting, what we're going to do is we're going to take this electron from the O, and we're going to transfer it over to the carbon. Now notice what that did is that freed up this electron to bond with this electron. And now we bond and we have our triple bond. Okay, I want to go over that one more time because I think it's a really important thing for me to show you. So we have the carbon and we have the oxygen. Okay. We bond, we hit a dead end. We ask ourselves, can we shift? In this case, we can shift because we can take this electron and we can shift it over here, freeing up this electron to bond with the carbon, and we end up with this as the Lewis structure for carbon monoxide, that as the Lewis structure for carbon dioxide. In part B, it says identify the shape of the CO2 molecule. Okay, so if you look on your chart, okay, this would be this. Okay, this is on page 64, because we have one central atom and 2 on the outside with no lone pairs. So that's called linear. I'm going to go ahead and go through a couple other things about CO2. In terms of sigma bonds, we're going to have 2 sigma bonds. In terms of pi bonds, we're going to have 2 pi bonds. And in terms of the hybridization, how many things are around this carbon? Things are letters or lone pairs. We have 2 letters, so that's going to be sp hybridized. Have a good day, guys. Take care.